Greetings, everyone. I am Uday Sharma from the Tripoli Department of Institute of Aeronautical Engineering. Today, I am going to discuss about the topic protection of low voltage DC microgrids. Low voltage DC microgrids are becoming increasingly popular in a variety of applications, including renewable energy integration, data centers, electric vehicles, etc. However, DC microgrids present some unique challenges for power protection due to their low inertia, high capacitance, and bidirectional power flow. Some of the key challenges for protecting the low voltage DC microgrids include high fault currents. That means the DC microgrids have low inertia and high capacitance, which can lead to very high fault currents, and also bidirectional power flow. In the DC microgrids, often have bidirectional power flow, which makes it more difficult to detect and isolate faults. Coordination. Protection schemes in DC microgrids needs to be coordinated to ensure that faults are isolated quickly and safely. Protection schemes. A variety of protection schemes have been proposed for low voltage DC microgrids. Some of the most common schemes include overcurrent protection, differential protection, traveling wave protection. Let us discuss overcurrent protection. The overcurrent protection is the most basic type of protection, and it is often used in conjunction with other protection schemes. Overcurrent protection devices operate when the current exceeds a time threshold. For the overcurrent protection to be activated in any sort of a grid or any sort of lines, there is a threshold limit of the current. Suppose for say 10 amps. If the 10 amps of the current, if the current exceeds more than the 10 amps, then the protection devices will be open and it isolates the device, it isolates the lines. Differential protection. Differential protection compares the currents at two ends of a line or a cable. The currents are different, then a fault is detected. Differential protection is very effective at detecting faults, but can be complex and expensive to implement. For suppose in a line, if the end of the line is sending something around 10 amps, for example, and the other end detects 0 amps, that means there is a fault in the between the line. So fault is detected. Traveling wave protection. Traveling wave protection detects the voltage and current waves that are generated by a fault. By analyzing the wave shape and arrival time of the waves, traveling wave protection can accurately locate the fault. Traveling wave protection is a very fast and accurate protection scheme, but it can be complex to implement. Overcurrent protection. Overcurrent protection is the most basic type of protection, and it is often used in conjunction, as discussed earlier, with other protection schemes. That is, it is often used in parallel with other protection schemes. Overcurrent protection devices operate with the current exceeds a certain threshold, as discussed. Overcurrent protection devices can be fuses or circuit breakers. Fuses are simple and inexpensive, but they can be reset once they have operated. They cannot be reset once they have operated. Circuit breakers can be reset, but they are more than expensive than fuses. A fuse is a device which blows out and isolates the two lines or two grids from each other, two systems from each other, and another fuse should be placed in the place of this fuse in order to again continue the line or close the line. But in the case of circuit breakers, the circuit breakers will fall down or switches off and isolates the two systems. And we can after solving the faults, after finding the faults and solving the faults, we can switch on the fault. We can switch on the circuit breaker to again continue the connection between the two systems. Differential protection compares the currents at two ends of a line or cable. The currents are different than the fault is discussed as discussed earlier. Differential protection is very effective at detecting faults, but can be complex and expensive to implement. There are two current measurement devices in and a communication link between the devices. Here, first there is a measurement device at the two ends of the line, and there is a communication link between the two devices. Here, if there is any fault, these two communicate with each other with this communication link. If there is a fault, if there is a fault in between the line, then they communicate with the communication link and say that there is a fault. DC microgrid protection devices. Let us see what are the different DC microgrid protection devices available. There are fuses, circuit breakers, protective relays, solid state circuit breakers, hybrid circuit breakers, and arc fault interrupter. And fuse is conventional and it is made of semiconductor. A DC circuit breaker is a molded case circuit breaker. It may be vacuum circuit breakers or hybrid solid vacuum. A protective relay is a DC power relay or digital relay. And there are different types of solid state circuit breakers such as gate turn-off thyristor, emitter turn-off thyristor, insulated gate bipolar transistor or IGBT, or insulated gate commutated thyristor or IGCT, or coupled coupled inductor as a solid state circuit breaker. And hybrid circuit breaker is a combination of DCCB or DC circuit breaker and a solid state circuit breaker. Arc fault interrupter. The arc fault interrupter or AFI is one of the form of protection devices used in the DC microgrid. Combination of arc fault circuit breaker is a combination of arc fault circuit interrupter. Grounding schemes. Grounding is also one of the important point to be noted while consideration of the protecting system. The grounding scheme of a DC microgrid can have a significant impact on the protection system. There are a variety of grounding schemes that can be used, including solid grounding, ungrounded, and high resistance grounding. In a solid grounding scheme, the negative pole of the DC microgrid is connected directly to the ground. This provides a low impedance path for the fault currents to flow, which helps to protect the power electronics and other equipment in the microgrid from overvoltages. However, solid grounding can also lead to high fault currents, which can pose a safety hazard. Ungrounded. In an ungrounded scheme, the negative pole of the DC microgrid is not connected to the ground. This eliminates the risk of high fault currents, but it can also make it more difficult to detect and isolate faults. Ungrounded schemes are typically used on only small or isolated microgrids. High resistance grounding. In a high resistance grounding scheme, the negative pole of the DC microgrid is connected to ground through a high resistance resistor. This limits the magnitude of fault currents. This limits the magnitude of the fault current while still providing a path for fault currents to flow. High resistance grounding is a good compromise between solid grounding and ungrounded, and it is often used in medium and large size microgrids. The best grounding scheme for a particular microgrid will depend on the specific requirements of the microgrid. For example, if the microgrid contains sensitive electronic equipment, then a solid grounding scheme may be required to protect the equipment from overvoltages. However, if the microgrid is located in a remote area, then a high resistance grounding scheme may be used to minimize the risk of electric shock. Fault current limiting devices. Fault current limiting devices can be used to reduce the magnitude of fault currents in a DC microgrid. This can help to protect the power electronics and other equipment in the microgrids. There are a variety of FCLDs or fault current limiting devices available, including fuses, circuit breakers, and solid state devices. As discussed earlier, fuses are the simple state of FCLD. They operate by melting a thin wire with a current exceeds a certain threshold. Fuses are inexpensive and easy to use, but they cannot be reset once they have operated. It should be replaced. Circuit breaker. Circuit breakers are more complex than fuses, but they can be reset after they have operated. Circuit breakers typically use a mechanical electromagnet mechanism to interrupt the current flow when a fault current occurs. Solid state FCLDs or solid state fault current limiting devices are the most advanced types of FCLDs. They are electronic components to limit the current flow during a fault. Solid state FCLDs are more expensive than fuses and circuit breakers, but they are also more reliable and faster. These are some additional considerations selecting FCLD for a DC microgrid. Bidirectional power flow, such as in a DC-DC microgrid, typically have bidirectional power flow, which means that the FCLD must be able to limit fault currents in both directions. High voltages. DC-DC microgrids can operate at high voltages, so the FCLD must be related for the appropriate voltage level. Fast response time. The DC-DC microgrid can have very fast fault currents, so the FCLD must have a fast response time to prevent damage to the equipment in the microgrid. Protection coordination. Protection coordination is essential for ensuring that the protection devices in a DC-DC microgrid can operate correctly during a fault. Protection coordination involves setting the operating characteristics of the protection device in such a way that the faults are isolated quickly and safely. There are a number of different factors to consider when coordinating protection device in a DC-DC microgrid, including the type and the location of protecting device, the expected fault currents, the desired level of selectivity. There are a number of different protection coordination schemes that can be used in DC-DC microgrids. One common scheme is used to combination of overcorrective protection and differential protection. Overcurrent protection is used to detect the isolate high fault currents, while differential protection is used to detect and isolate low fault currents. Another common protection coordination scheme is used to hierarchical structure. In a hierarchical structure, the protection devices are arranged in a series or levels, with each level protecting a smaller portion of the microgrid. The protection device at the lower levels are set to operate first, followed by the protection devices at the higher levels. This ensures that the faults are isolated quickly and safely. Protection in renewable energy integration. Renewable energy sources such as solar and wind are often integrated into low voltage DC microgrids. However, renewable energy sources can introduce new challenges for protection. For example, solar and wind sources are reliable and variable and intermittent, which can make it difficult to maintain a stable voltage and frequency in the microgrid. Additionally, renewable energy sources can generate harmonics which can cause high interference with the other equipment in the microgrid. To protect low voltage DC microgrids with renewable energy integration, it is important to use protection schemes that are designed to handle the unique challenges of renewable energy. For example, protection schemes should be able to connect and detect and isolate faults quickly, safely, even in the presence of variable and intermittent generation. Additionally, protection schemes should be able to filter out harmonics and other interference caused by renewable energy sources. Thank you. This is Suresh Sharma signing off.